Welcome back. Today, at long last, we reach the fundamental theorem of calculus. What we will do today depends heavily on the previous video, where you learned about the notion of an accumulation function, and you learned the antiderivative lemma. The fundamental theorem of calculus comes in two parts, which you might say are like two faces of the same coin, though I prefer a different metaphor which I use in the book. I like to think of the two versions of the fundamental theorem as the acorn version and the oak version of the fundamental theorem. Each, in some sense, contains the other, but when you see an acorn, it's very hard to appreciate what will ultimately grow from it. We will start with the acorn version, which concerns the accumulation functions you learned about in the previous video. In particular, the FTC acorn is about the derivative of an accumulation function. And rather than just stating the result and then explaining why it's true, what I want to do here is just think it through step by step so that we can arrive at the result together. So let's begin with a very quick review of accumulation functions themselves. Recall that an accumulation function is based on two things. First, some function, which I'll just call f, and second, some starting point in the domain of the function, which I will call a. Those two things determine a new function, which I'll call capital A for accumulation, that works as follows. If we feed this accumulation function some input value x, like this, what the accumulation function does is it integrates this function f from the starting value a until we reach the stopping value x. So if we wanted to write down a formula for the accumulation function, it would look something like an integral of f from a to x, but as we discussed at the end of the last video, I can't just write f of x dx right here, because I can't integrate as x runs from a to x. I can't say start adding when x is a, that part's fine, and stop adding when x is x. That doesn't make any sense because x is always x. So we have to use a dummy variable right here. We typically write f of t dt. So the argument of the accumulation function, the input value, simply becomes the upper boundary of integration of this integral of f. And in particular, in this picture here, a of x would correspond to this area, because of course this integral represents that area. Okay, so far so good. I should mention that in the previous video, I included some subscripts here and wrote a of x as a sub f a x, where f corresponded to the function and a corresponded to the starting point, but I'll typically leave those off in this video now that you know what accumulation functions are all about. The function and starting point will, generally speaking, be obvious, but if we ever need to specify them, I will write them out explicitly. Okay, so much for the review of accumulation functions. The fundamental theorem of calculus in its acorn version tells us something about the derivative of an accumulation function. And maybe I should be slightly more specific here. It's going to be about the derivative of an accumulation function for f, where f is any old function. Now, remember, any old function f can generate infinitely many different accumulation functions, because I could choose anything in the domain to be the starting point. But the statement of the fundamental theorem of calculus in its acorn version concerns the derivative of any of them. It turns out they will all have the same derivative, which will make perfect sense in a moment. All we have to do is think about this geometrically and think about the meaning of a derivative. And if we do that, we'll be able to write down the result we want very easily. So given this setup right here, let's think about the derivative of the accumulation function. This isn't a mechanical process. This is about thinking about what a derivative means. And as I hope you remember, a derivative is a ratio of infinitesimal changes. We change the input value by an infinitesimal bit, we increase that, dx, and that induces a little change in the output, dA in this case. The ratio of the infinitesimal change in the output to the infinitesimal change in the input turns out to be a real number, and that real number is our derivative, our rate of change. Change in the output over change in the input on an infinitesimal scale. Well, we can think about what both of these things mean geometrically. So let's set it in motion. Okay, we're going to give a little nudge to the input value. So instead of starting at x, we're going to move over by an infinitesimal amount, dx. Now, obviously, I can't draw an infinitesimal amount, so this will just be a schematic picture, but you have to imagine something infinitesimally close to x. So that point is at x plus dx, and that little infinitesimal change between the two values is, of course, dx, the infinitesimal change in input. Okay, well, how does that change the output? Not the output of f, but the output of a, the accumulation function, because that's the function whose derivative we're looking for. Well, we already interpreted the output a of x as an area. So if I slide this x over just by a little infinitesimal amount, the new output will be a new area. It won't be the area under the curve between a and x. It'll now be the area under the curve between a and x plus dx. So all the area that was there before is still there, and then I get this infinitesimal bit of area tacked on the end. This is a little infinitesimal rectangle. So instead of problems in the past where we chopped a region like that up into infinitesimal rectangles, we're just scooching this over a little bit just to pick up one of them. Anyway, what can we say about the area of that infinitesimal rectangle? Well, we can say two things. First of all, that's the extra little bit of area we picked up when we increased the input by an infinitesimal amount. That little bit of area adds on to the area that was already there. So this area represents the infinitesimal change in output of the function a. In other words, that area is dA, the infinitesimal change in output. But I said there were two ways we could think about this area. On the one hand, sure, it's dA. On the other hand, well, this is an infinitesimal rectangle. What's the area of a rectangle? It's the base times the height. What's the base? Dx. What's the height of this rectangle? Well, it's standing here at x, and it goes up to the graph of f. So the height of that thing is f of x. What we've just seen is that dA, the infinitesimal change in output, is the area of this rectangle. But the area of that rectangle is f of x, the height of the rectangle, times dx, its width. So I'm going to rewrite that dA as f of x dx, and I'll carry the dx downstairs over. Now I have dx's upstairs and downstairs. They cancel, leaving me with plain old f of x. Ah, that's very nice indeed. Look at what we have just discovered. If we start with a function f, form an accumulation function from it, then take the derivative of that accumulation function, what we get back is the function itself. So essentially, the operations of forming an accumulation function, which is really integration, and differentiation are inverses to one another. They undo one another. And that is the content of our Acorn version of the fundamental theorem of calculus. So let me fill this out. The derivative of any accumulation function for f is f itself. Hooray! We've got the fundamental theorem. But not everyone is satisfied. What does that mean? So what? Who cares if the derivative of an accumulation function for f is f itself? I mean, maybe it's kind of interesting that differentiation sort of undoes integration, but so what? Does this actually accomplish anything for us? In what sense is this fundamental? Does it really deserve that f? I mean, what is this pitiful little acorn? Nothing can grow from that, right? Well, something very big can grow from this acorn. You just have to put it in the soil of the antiderivative lemma. So let me remind you of what the antiderivative lemma says. It says that antiderivatives of the same function can differ only by a constant. There's also some fine print that says that the antiderivatives have to have the same domain, but I just want to remind you of the main gist of the lemma, which tells us, for example, that since sine is an antiderivative of cosine, any other antiderivative of cosine can only differ from sine by a constant. So cosine has other antiderivatives like sine of x plus 9 or sine of x plus 14, but those are the only sorts of antiderivatives that cosine has. Such is our antiderivative lemma. And I have claimed that when we combine these two things, the Acorn FTC and the antiderivative lemma, we get some marvelous results that we couldn't get otherwise. So I want to demonstrate this to you by returning to an old problem that I posed way back in the first video in this series. Namely, what is the area under one arch of the sine wave? So we're looking for this area right here. And I mentioned in that earlier video that this is a difficult problem because of that curve. We know how to find the areas of polygons, that is, figures with straight sides. We just triangulate them, chop them into triangles, and find the areas of the triangles and go from there. The problem is finding areas of things with curved boundaries, like the area in question. And I noted in that earlier video that you know how to find the area of a circle and maybe an ellipse, and that's about it for figures with curved boundaries. And of course, we discussed how to express an area like this in terms of an integral by chopping it up into infinitely many infinitesimally thin rectangles so that the area we seek is the integral of sine as x runs from 0 to pi, because a typical infinitesimal rectangle at x, any value between 0 and pi, is going to have a height of sine of x, obviously, and a width, an infinitesimal width of dx. So that rectangle's area is its height times its width, sine x dx, and that's what we have right here. So the stuff in the red box represents the area of one of those rectangles, and we're going to add all of them up as x, this point right here, runs from 0 at this end all the way out to pi at this end. Add up all those infinitesimal areas of those rectangles, and we get the area of the whole arch. Okay, that much we know, but how do we actually evaluate that? How do we turn that integral into a number? Well, here's the idea. First, I want to loosen this expression up a little bit. When we are studying calculus, we like things to have a little play in the joints so that things can change. This is the mathematics of change, after all. We need to be able to increase one variable by an infinitesimal amount and see how that affects another variable, and so on and so forth. So rather than getting right up to this thing and saying, well, the area of that thing is that, now how do I get to that? Let's just take a step backwards and look at something related to this, not quite the same thing. Instead of just thinking about the sine function itself and the integral of the sine function from 0 to pi in particular, let's relax that specificity a little bit and look instead at the accumulation function for sine, which integrates sine not just from 0 to pi, but from 0 to whatever. You give me any input x, and the accumulation function for sine gives you a of x, the area under the curve from 0 to x, the integral of sine from 0 to x. So that the integral we actually want, which gives us the area under one full arch, is in fact capital A of pi, where capital A is this accumulation function. Because of course, if we evaluate the accumulation function at pi, we get all the area from 0 up to pi, which is exactly what we were looking for. Well, okay, you might say, fine, that makes sense, but how does it help us? Well, our strategy is going to be to come up with an explicit formula for A. I don't mean just in terms of an integral. I mean in terms of something we can compute. And once we have that explicit formula for the accumulation function, we will be able to evaluate it at pi in the ordinary way. And then we'll have the area we want. We'll do this by making a series of observations. First, what do we know about this function A, this accumulation function for sine? Well, the FTC Acorn tells us something. It tells us that a of x, the accumulation function, is an antiderivative of sine x. Be sure you see why this follows from the FTC Acorn. It tells us that when we take the derivative of some accumulation function for a given function, we get the given function back. So that means the accumulation function for any given function, sine in this case, is an antiderivative of that function, because when we take the derivative of the accumulation function, we get the function itself. Okay, so that's the contribution of the acorn. Let's make another observation. Minus cosine x is another antiderivative of sine x. Well, that's just something everybody knows. You take the derivative of minus cosine and you get sine. Okay, so what's the big deal? We have found two different antiderivatives of sine. Oh, this is where that nourishing soil of the antiderivative lemma can work its magic on our little acorn, because the antiderivative lemma tells us that any two antiderivatives of the same function can differ only by a constant. Well, here we have two antiderivatives of the same function. So that means that we know something about our accumulation function. The only form it can take is minus cosine x plus a constant. That is what the antiderivative antiderivative lemma guarantees. That same antiderivative lemma that we proved 2 different ways in the last video. Ah, now that is interesting, because now I have an expression for the accumulation function, or part way to an expression for an accumulation function, that doesn't explicitly involve an integral. It's minus cosine x plus some constant. Ooh, if only we knew what that constant was. But how can I find it? How can I find the value of c? Can I do it? Yes, we can. If we can think of some value of x for which we know the exact value for minus cosine x, and more importantly, that we know the exact value of a of x, then we can plug that value of x in, and we'll have an equation of some number is some number plus c. And so then we can just solve for c. Ah, that's good. But is there such a value of x? I mean, that would need to be a value of x where we know a of x. You might say, oh, that brings us right back to where we started. I'm trying to find a of pi. I don't know the value of the accumulation function anywhere. Oh, but we do. We know its value when x is 0. When x is 0, this becomes a of 0 is minus cosine of 0 plus that same constant c. But a of 0 is, of course, 0 because there's no area to accumulate. And cosine 0, well, 2 seconds of thought about the unit circle tells you that that is going to be 1. So 0 is minus 1 plus c, which of course means that c is 1. Thus, what do we know about our function a of x, our accumulation function? It can only be minus cosine x plus 1. So coming back to our original expression for the area under one arch of the sine wave, the accumulation function evaluated at pi is minus cosine pi plus 1 by this formula we just found. And another 2 seconds of thinking about the unit circle tells us that cosine of pi is, of course, minus 1. So this all becomes minus 1 plus 1, which is 1 plus 1, which, and this may be the hardest part of the entire course, is 2. Whoa, we did it! We have found the area under one arch of the sine wave, despite that curvy boundary. Please take some time to run through this argument on your own and make sure you understand it. It's kind of amazing how all these pieces come together. It's really a beautiful line of attack on this problem. I hope you can appreciate how clever it is. And then as an added bonus, the specific result, the area under one arch of the sine wave, is 2. That's weird. It is not, at any rate, what most people would guess. After all, sine is defined in terms of circles, the unit circle we've referred to a couple times. Where there are circles, there is pi. So I think most people would guess that this area has something to do with pi, but it doesn't. In fact, it's a whole number, 2. What could be simpler? So an interesting result obtained by very interesting means. Okay. Now, in principle, the strategy we used there, combining the Acorn FTC and the antiderivative lemma to evaluate this specific integral, that strategy can, in theory, be used to evaluate any integral. In practice, there are some difficulties. But just to emphasize that this strategy will work in theory on any integral, let's do one more specifically like this. And then we will combine these two statements in the abstract, not on a specific problem, and that will allow us to get the Oak version of the fundamental theorem. But one more example using the Acorn. So a new problem. Evaluate this integral, the integral of 5x cubed as x runs from 1 to 2. Now we could, if we wanted to, interpret this as an area, but let's not even bother. Let's just see how this technique would work. Our solution is going to come the same way. We start with 2 different antiderivatives of the function that we are trying to integrate. One way to get an antiderivative of any function, of course, is to just form the accumulation function. So our accumulation function, which is going to be an integral not from 1 to 2, but from 1 to x of our function, is going to be an antiderivative of that function. But remember, I have to be careful. I can't write 5x cubed dx here, because then I would be starting my sum when x is 1 and stopping it when x is x. But x is always x, so that doesn't make any sense. So I use a dummy variable. My function is the thing that cubes the input and then multiplies it by 5. Well, I could call that 5t cubed just as well. So then I let t be my dummy variable. And now I've got an expression for the accumulation function. This accumulation function is an antiderivative of 5x cubed. Another antiderivative of 5x cubed is, of course, 5x to the fourth over 4. It's the usual trick. We raise the exponent by 1 and divide by the new exponent. So by the antiderivative lemma, the accumulation function must be 5x to the fourth over 4 plus some constant c. What's the constant? Well, I could figure it out if I can find some value of x that I can pop into this equation and turn these things both into ordinary numbers. Then I can just solve for c. Well, any value of x will do on the right side, but what's a value of x that I can actually evaluate this accumulation function at? Well, it's the same thing as we did last time. If we make the upper boundary of integration the same as the lower boundary of integration, then we're not accumulating anything, and the value of the accumulation function would be 0. So let's do that. Let's let x be 1. When x equals 1, this equation becomes a of 1 is 5/4 plus the constant. But as we said, a of 1, that's integrating something starting when t is 1 and stopping when t is 1. So we never get anywhere. So a of 1 is 0 because our poor integration demon had nothing to accumulate. But if 5/4 plus c is 0, then c must be minus 5/4. So a of x, our accumulation function, which we already found has this form, must be 5x to the fourth over 4 minus 5/4. Thus, at long last, since we have an expression for our accumulation function, we may conclude that the integral that we're looking for, which of course I can write this way instead, because as we discussed in the last video, this t is just a dummy variable, just as the x was. In both cases, we're just integrating the function that cubes the input and multiplies by 5 from 1 to 2. Doesn't matter whether we call it t or x or red box or q or smiley face or whatever. But when we integrate that function from 1 to 2, well, that's like putting a 2 here in the accumulation function. So we could say that this is equal to capital A of 2, which in turn we can evaluate using the formula we just found. So popping a 2 in there, we get 5 times 2 to the fourth over 4 minus 5/4. Factor out of 5/4 to make the arithmetic easier. 2 to the fourth, 2, 4, 8, 16 minus 1, so that all becomes 15. 15 times 5 is 75, and we have it. This integral with which we started is equal to 75 over 4, precisely. Good, and I hope by now you see how this could, as I said, in theory, be done to evaluate any integral. Remarkable, but it seems kind of complicated. Well, don't worry, the complication will become much simpler shortly. That is what the Oak version of the fundamental theorem of calculus does. It takes what we have done right here and in the previous problem and automates it so that all the complicated stuff goes on under the hood. Now the metaphors are getting hopelessly mixed. We've got trees and cars all mixed up. Well, such is life. But one thing I do want you to observe here is how crucial it was in the process, whether we do it out carefully using this Acorn or whether we automate it with the Oak version, how crucial it was for us to be able to come up with an antiderivative of the function we were trying to integrate. That will still be the central part of integration. What the Oak version does is basically hide all the rest of it and reduce the whole problem down to finding some antiderivative. Okay, I think you've got the idea, and now it is time to move on to that mighty Oak. I'm going to go ahead and start writing down the fundamental theorem of calculus in its Oak version, which after a while we will just call the fundamental theorem of calculus. So, if f is a continuous function over some interval on the real line a to b, notice how general this is. We just can't have functions with breaks in their graphs. And capital F is a known antiderivative of little f, then the integral of f over the interval from a to b is equal to, well, we shall see. We will fill that in soon. Once again, rather than just announcing the result and then proving it, I want to lead you to the result so that you come upon it naturally. So let's just mess around below that green line and see if we can figure it out. Given this setup, let's make some observations. We'll start, as we did in those previous problems, by identifying two antiderivatives of f. One is, of course, this accumulation function. That guy is an antiderivative of f, but so is capital F, this other known antiderivative. So let's just say that this accumulation function and capital F of x are both antiderivatives of little f. Hence, the accumulation function can only be the known antiderivative, capital F, plus some constant, which we'll call c. All right, but can we figure out the value of c? Sure we can. We just need some value of x where we can evaluate these functions. Now f is a known function, so of course capital F of anything, we can handle that. But we need some value of x that we can stick in this accumulation function and make sense of it. And of course, having watched the previous two examples, you know exactly what we're going to do. The x we're going to choose is little a, because when x is a, this previous equation becomes capital A of little a is capital F of little a plus c. But why did we choose a? It's because we know what capital A of little a is. When we stick little a into this accumulation function, we're integrating a function from a to a. Well, there's nothing to accumulate. So capital A of little a is going to be 0. And I can solve this for c. c is the negative of capital F a. Thus, if we go back to our equation for the accumulation function that we got by the antiderivative lemma, of course, substituting that value of c in there tells us that capital A of x is capital F of x minus capital F of a. Well, now we are basically done, because the integral we want, which I'll rewrite down here, this integral we're trying to find, which of course I could rewrite as integral of f of t dt instead of f of x dx, as t runs from a to b. I recognize that this integral is capital A of b, because popping b in there gives me the integral of f of t dt as t runs from a to b, and that's exactly what I have right there. But to get a of b, well, we just stick b into this formula and we come up with capital F of b minus capital F of little a. Let's record that up here. Capital F is a known antiderivative of little f, and the integral of little f from a to b is that antiderivative evaluated at the upper boundary of integration minus that antiderivative evaluated at the lower boundary of integration. And that is the full fundamental theorem of calculus in its oak version, wrapped up in royal purple. And I hope you have appreciated how the acorn placed in the soil of the antiderivative lemma leads directly to the mighty oak. It is interesting on many levels. It tells us that to evaluate an integral, we need to find an antiderivative of the function we are trying to integrate. When you first met the idea of an integral as an infinite sum of infinitesimals, who would ever have guessed that derivatives had anything to do with them? Remarkably, it also tells us that all we have to do is evaluate that antiderivative at the endpoints of the interval over which we're integrating. That seems too good to be true. After all, we're adding up infinitely many infinitesimals. We're running across every real number from a to b, infinitely many of them. And in the end, that sum turns out to depend only on the endpoints. Remarkable. I want to give you some examples of how this works, but there's one last thing I want to show you, which is some very important notation that we use when we are actually using the fundamental theorem of calculus. I'll write it in the corner. If we have some antiderivative that we found, which I'll continue to call capital F of x here, and we put it in brackets and then write a little a subscript and a little b superscript, that notation simply means evaluate the function at the top, evaluate the function at the bottom, and subtract. It might seem silly to have special notation for that, but it's very convenient when we're using the fundamental theorem of calculus in practice. Let's do a few examples and you'll see what I mean. Let's say we want to integrate the function square root of x from 1 to 4. Now, such an integral could arise in any of a million different ways, some of which we talked about in the early videos, but we're not worried about that. We just want to know, how do we evaluate it? Well, what does the fundamental theorem in its oak version tell us? And from now on, I'm just going to call it the fundamental theorem. What does the fundamental theorem tell us? It says that miraculously, this infinite sum of infinitesimals can be found by finding an antiderivative of the original function and then evaluating it at these two endpoints and subtracting. So to use that notation that I introduced a moment ago, this integral is equal to, well, whatever I could get if I find some antiderivative. I'm going to put the brackets there waiting for it and evaluate that bracket notation at 1 and 4. All I have to do is fill in the appropriate antiderivative. So what is the antiderivative of square root of x? Well, it's a power function. I just have to remember this is x to the 1/2 power. I know how to find the antiderivative. We just raise the power by 1, so that'll be 3/2, and divide by the new power. But dividing by 3/2 is the same as multiplying by 2/3, so I'll do that. So this equal sign holds because of the fundamental theorem of calculus. That's where the miracle happens. The rest is just arithmetic, because now all I have to do is evaluate and subtract. Let's carry it out. this stuff becomes 2/3 of 4 to the 3/2, if that's what happens when we stick the 4 in for x, minus 2/3 1 to the 3/2. That's what happens when I stick in the 1, the lower boundary, for x. This is just arithmetic. Let's factor that 2/3 out to make life easier. And now I just have to think, well, 4 to the 3/2. It's the cube of the square root of 4. So that's the cube of 2, so that's 8. And 1 to the anything, of course, is 1. So this all becomes 8 minus 1, which is 7, multiplied by 2/3, and I get 14/3. And we are done. Impressive, is it not, this fundamental theorem of calculus? Faced with the problem of evaluating this infinite sum of infinitesimals, we did it in one line. Let's do another example. Let's integrate 1 over x as x runs from 1 to e. Okay, how are we going to do this? Well, of course, we're going to use the fundamental theorem of calculus. And that just entails thinking of an antiderivative for the function we are trying to integrate. Can I think of an antiderivative for 1 over x? Sure, that's log of x. Everybody knows the derivative of the natural logarithm is 1 over x. And I've already slapped the brackets on, and I need to put those boundaries on, 1 and e, and so this is log of e minus log of 1. And while I would like to think that anybody taking an integral calculus class can do those unconsciously, experience tells me that that is not always so. But of course, these are trivial to evaluate provided you know what the natural logarithm actually means and not just as a button on your calculator. The log of anything is the power you have to raise e to get anything, whatever the input was. If you don't know this, you don't understand logarithms. That's the definition of the function. Anyway, log of e. What power do I have to raise e to get e? Well, obviously that's 1. E to the 1 is e. So that first term is 1. And what about the second one? Log of 1. Well, that's the power I have to raise e to get 1. What power do I raise e to get 1? Of course, it's 0. E to the 0 is 1. So this is 1 minus 0. And the answer to that challenging conundrum is just 1. So this integral, this infinite sum, this weighted sum of infinitesimals, when all the dust settles, shakes out to be 1. I think we can squeeze one more in here before I have to erase anything. How about the integral of 1 over 1 plus x squared from 1 to root 3? Well, now I think you see why you need to know your antiderivatives, which of course means why you need to know your derivatives. What function has a derivative equal to 1 over 1 plus x squared? Ah, good. You remember, it's arctangent of x. So that is the magic function that we have to evaluate at the endpoints and subtract, and then by this miracle known as the fundamental theorem of calculus, which isn't really a miracle, we've seen why it works after all, but anyway, by this remarkable theorem, we will know the exact value of that complicated weighted sum of infinitesimals. So what's this going to be? Well, this is arctangent of root 3 minus arctangent of 1. And again, I would like to think that anybody who has gotten this far in calculus can evaluate those expressions with no problem, especially this one. But the sad truth is, what I would like to think does not always correspond to what reality serves up to me. So again, what does arctangent mean? The arctangent of anything is the angle between minus pi over 2 and pi over 2, whose tangent is whatever number you stick in. Everyone should know the arctangent of 1 off the top of your head, of course. That one is geometrically obvious. What's an angle whose opposite over adjacent is 1? Well, that means the opposite and adjacent are equal. That means we've got a right isosceles triangle. Well, that's obviously 45 degrees, or, as we say in calculus, pi over 4. But what about this one? Again, it should be familiar to you. It's not connected with right isosceles triangles, which are half of a square. It's connected with that other kind of triangle that you think about all the time in trigonometry. A 30, 60, 90 triangle, which is half of an equilateral triangle. So you have the half square and the half equilateral triangle. Those are your two triangles that all your basic special angles come from. And what are the side ratios on that triangle? Well, if we call the short side 1, well, that's half of the full side of the equilateral triangle, which must therefore be 2 units long. Ah, but this is another side of the equilateral triangle, so that must be 2. Oh, and if we know 2 sides of a right triangle, like this one, of course we can get the third one, thanks to Pythagoras. By the Pythagorean theorem, that remaining leg would have to be square root of 3. Ah, that's the old familiar triangle. What's an angle whose tangent is square root of 3? Here's an angle, its opposite is root 3 and its adjacent is 1. Ah, so its tangent is square root of 3 over 1, which is square root of 3. So that arctangent is 60 degrees, or as we call it in calculus, pi over 3. And we do this arithmetic and we get pi over 12. Hooray, we've got another one. And you are seeing the importance of knowing how to find antiderivatives quickly, and of course knowing your basic pre-calculus as well. Even very simple functions like the square root or the reciprocal function or this rational function have antiderivatives that in order to evaluate them, you have to think about the meanings of various things. Like, what does it mean to raise something to the 3/2 power? What does it mean to take the natural logarithm of something? What does it mean to take the arctangent of something? So you have to know your pre-calculus, you have to know your calculus 1 so you can get your antiderivatives. But when you put them all together, this fundamental theorem makes things very, very easy. Notice how clean and crisp everything comes out compared to when we were doing everything with our bare hands, as it were, combining the fundamental theorem in its Acorn version with the antiderivative lemma. That's all going on here too, but it's all, as I said before, under the hood of the big version, the Oak version of the fundamental theorem of calculus. All we have to do to use it is come up with an antiderivative. That's why we like antiderivatives. We use them every time we want to evaluate integrals, and as we saw in the earlier videos, integrals come up all over the place. You might find it instructive to go back and redo those two earlier integrals that we evaluated with the FTC Acorn and the antiderivative lemma before we had our Oak version. You can now redo those two integrals using the FTC Oak and confirm that you will get the exact same results, but this time you will get them much, much, much more easily. It is very nice to pack all that logic under the hood. Let's do a few more examples. The integral of cosine 3x from 0 to 2 pi over 3. Well, we have to find an antiderivative of this function. Ah, you're an old pro at that. That's what we talked about in the last video. We can come up with an antiderivative of that function by using the old guess and adjust trick. I mean, forget about the 3x. The outer function here is cosine. So we expect the antiderivative to be something like sine of 3x. Is that right? Well, think it through. If I took the derivative of this guy, I'd end up with cosine of 3x. Oh, but the chain rule means I'm going to get an extra 3 out front. I'd get 3 cosine 3x. I don't want that 3 there. I can balance it out, however, by putting a 1/3 here, because when I take the derivative of all this stuff, the 1/3, the constant multiple, just sits there. And the derivative of this, we already realized, is going to be 3 times what we're actually aiming at. Well, that 3 will cancel with that 1/3 and give us what we want. So yes, this is the antiderivative we want. Pop those brackets on there, and we're in business. Oh, I'll show you a little trick. When you have a constant multiple inside this bracket notation, you can actually pull it outside of the brackets. So I could rewrite this as 1/3 of sine 3x in the brackets, evaluated at 0 and 2 pi over 3. Hey, why can you do that? That's an exercise in the book, so you'll do that for homework. Very easy to explain why that works. Anyway, we'll take it on faith here. When I evaluate this bracket notation, I get 1/3 of sine 2 pi minus sine of 0. Oh, that means this is 0 minus 0, so this is 1/3 of 0, which is 0. Hey, that's weird. You're telling me this infinite sum of infinitesimals here is somehow equal to 0? I don't believe you, so you might say. But actually, this makes perfect sense. Think about what the graph of this thing looks like. Any calculus student should be able to graph this with ease. Don't let the 3x fool you. You know what the graph of plain old cosine x looks like. Something like this. Of course, it starts at 1, and it has a period of 2 pi. But wait, we're looking at cosine of 3x. Substituting 3x for x in an equation. What does that do to its graph? That is a horizontal stretch, or a compression, or a smush, or whatever you want to call it. It pulls everything back to 1/3 of what it was before. So instead of having this second peak be at 2 pi, it is now at 2 pi over 3. Ah, so that's the basic picture of y equals cosine of 3x. Now, why does that explain geometrically why this integral should be 0? Well, think about it. If we're integrating this function from here, 0, out to 2 pi over 3, what happens when we send our integration demon in to do his infinite sum? Well, he starts here at 0 and adds, getting all these positives. But then when he gets to this point, it switches to negative, so that starts eating away at the running total. More negatives, although they're getting smaller. And then he reaches this point and it starts getting positive again. Well, look, by the symmetry of the graph, we should see, even though my graph is terrible, that this area up here matches this area exactly. And similarly, this area over here matches this area exactly. So all the positive stuff that he's accumulated up to this point gets balanced out exactly by that. So by the time we integrate to this point, which would be, what, pi over 3, we would have a running total of 0. Then it would be negative for a while. If we stop the integral right here, the running total would be a negative value. But we don't. We keep going. We add on all those positives, and those positives balance out with those negatives, just as those positives balance out with those negatives. So the total really does turn out to be 0, as we can see. Good. As a final example, let's work with a class of functions that is stupendously easy to integrate. Polynomials. They're the easiest functions in the world to integrate because the antiderivatives are so easy to find. And this is because antiderivatives can be found term by term, just like derivatives you can take term by term. You'll prove this in the exercises in the book as well. Again, it's easy, but let's just take that as read here. So let's just integrate some polynomial from 0 to 1. Here I've got 3x cubed minus x squared plus 2x plus 1. We just need to think of an antiderivative of that. Well, as I said, you can get antiderivatives term by term, and every term has a very easy antiderivative. Those are the first kind of antiderivatives we learn to take. So we should be able to write this down very simply. Antiderivative of the first term, well, that's going to be 3x to the 4th divided by 4. So I'll go ahead and write that down, 3x to the 4th over 4, minus x squared. Let's see, antiderivative, that's going to be minus x cubed over 3 plus 2x. Well, that's 2x squared over 2, which of course is just x squared, plus 1. What's an antiderivative of 1? Well, that's x, of course. Oh, that's it. We've got our antiderivative, so pop on the bracket notation. Now we just have to do some arithmetic. Well, when we put in the 1 for x, we get 3/4 minus 1/3 plus 1, and from that, we have to subtract the result when we pop 0 in for all those x's. Oh, but when we pop 0 in for all those x's, of course, we get 0. You ask your favorite 4th grader to do the arithmetic for you, and he or she gets 29 over 12. The end. And any polynomial in the world is just as easy to integrate. Okay, that's enough examples. There are more in the book as well, of course. I want to finish this off just by mentioning a few algebraic properties of integrals. These are also things that you will prove in the exercises, but there's no reason why I can't at least state them here. Let's start with what are usually called the linearity properties of integrals. This name, linearity properties, might be familiar to you from other contexts. If it is, then you can probably guess what these properties are. For example, you have met the linearity properties of derivatives, whether or not you knew them by that name. They are 1. The derivative of a sum is the sum of the derivatives. In other words, we can take derivatives of a sum term by term. The second linearity property of derivatives is that if you have the derivative of a constant multiple of a function, you can pull that constant multiple through the derivative operator so that you get the constant times the derivative of the plain old function. So we can take derivatives term by term, and we can pull constant multiples through the derivative operator. Take those statements, strip away everything we said about derivatives, and insert integrals, and you have the linearity properties of integrals. Namely, integrals can be done term by term, and also constant multiples of functions can be pulled through the integral sign. You'll explain why both of these are true in the exercises. Neither is hard if you just think of each integral as an infinite sum of infinitesimals. Doing so will make both of these properties very intuitive. For example, consider this second one. On the left, we have an integral, an infinite sum in which every term shares a common factor of c. It should therefore be intuitive, from your knowledge of factoring from basic algebra, that you can factor that c out of the sum, i.e. factor it out of the integral, thereby obtaining the expression on the right. And a similar sort of intuitive argument should convince you that this one is true as well. Essentially, you're just adding up the same stuff 2 different ways. I'll leave it to you to convince yourself of that. I'll give you a quick example of how one might use these things. First, spelling everything out in awful detail, and then as we would probably actually do it in practice. So, suppose we want to integrate e to the 3x plus 2 cosecant squared x from pi over 6 to pi over 3. Well, if we wanted to do this the long, gory way, which you might if you want to break it into bite-sized pieces, we could proceed as follows. We recognize, oh, I've got the integral of a sum, so by the first linearity property, I can break that into the sum of 2 separate integrals. In other words, we're going to integrate this guy term by term. And then, in fact, in this second one, we might recognize, oh, I've got this constant multiple here. Well, by this second linearity property, I can pull that through the integral sign. I'm going to go ahead and do that here to save a little space. So now I have that my original integral is the sum of these 2 other guys by the linearity properties of integration. And then, of course, I could do these separately, feeling comfortable in the fact that I have two relatively straightforward integrals, which don't look as messy as this whole thing. So I will just say, etc. That's kind of the long way of doing it. It's a little longer because at the end of the day, after we use the fundamental theorem of calculus on each separate integral, we have to evaluate the antiderivative of each separate integral at the various endpoints and so on and so forth. And it might be worth your while to actually carry out the details just to see what I mean. But in practice, we would probably do it slightly differently, so I will show you what I mean by that. So let's get rid of this stuff and start over. What I am going to use is the fact that not only integrals have these linearity properties, and not only derivatives have those linearity properties, but antiderivatives obey the linearity properties. The linearity properties of antiderivatives follow immediately from the linearity properties of derivatives. Antiderivatives can be taken term by term, and to get an antiderivative of a constant multiple of a function, we just multiply that constant by any antiderivative of the function itself. And again, these are really obvious if you think about them. For example, why is the second one true? Why is this an antiderivative of c times f of x? Well, if I take the derivative of this thing, I know by the linearity properties of derivatives that it's going to be c times whatever the derivative of this is. And what is the derivative of this? Well, of course, it's going to be f of x, because this thing in the box is an antiderivative of f of x. So when I multiply by c, I get c times f of x. So yes, indeed, this is an antiderivative of that thing. Similar kind of argument works for the top one. Okay, but anyway, let's apply that here. Rather than formally breaking this into two separate integrals, let's just come up with an antiderivative of this thing all at once and use the fundamental theorem right away. We can do that pretty easily because we know that antiderivatives obey the usual linearity properties. So to find an antiderivative of this thing, it suffices first to find an antiderivative of the first term, then let the two just sit there and find an antiderivative of the second term. Put it all together and that'll be an antiderivative of the whole thing. So let's try that. What's an antiderivative of e to the 3x? Well, this is a classic guess and adjust kind of thing. It's an exponential function, and we know that an antiderivative of e to the whatever is e to the whatever, but we do have to worry about the chain rule. So we know the antiderivative is going to be something like e to the 3x, but not quite, because if I take the derivative of this thing, I get e to the 3x times 3 because of the chain rule. Well, there's no 3 up here. So to balance that 3 out that I get by taking the derivative, of course, I have to put in a 1/3. Okay, good. So that's the antiderivative of the first term. Well, good thing we can take antiderivatives term by term, because that means I can just now take the antiderivative of this one. And in fact, hey, I can let that constant multiple just sit there. So let me just go ahead and put the +2 there. And now I just have to think, well, what's an antiderivative of cosecant squared? Well, this is where I have to think back about our derivatives of the trig functions. Ooh, if it was secant squared, I would know it was tangent. Oh wait, we know that derivative of tangent is secant squared, so now I remember if I have cotangent and I take its derivative, what do I get? I get the minus because of the co, and then it's like the derivative of tangent, it's like secant squared, but all the trig functions become cofunctions. Oh, so that's cosecant squared. Hey, that's really close. If I take the derivative of cotangent, I get minus cosecant squared. Ooh, I was just aimed at cosecant squared. Well, how can I balance that out? Oh, I know. Instead of taking the derivative of cotangent, I'll take the derivative of minus cotangent, because then that factor of -1 just sits there and cancels with that minus, and I get what I'm aiming at. The derivative of minus cotangent is cosecant squared, just like I like it. So that means an antiderivative of cosecant squared is minus cotangent x. And of course, I have to put the boundaries of integration on my bracket notation, like so, and the ugliness of this thing gives me the fidgets, so I'm going to go ahead and rewrite that as -2 cotangent x, and now I just have to evaluate, and I'm done. When we pop in pi/3 for x, we get this stuff, and when we pop in pi/6, we get this stuff. I wrote this out just to emphasize that you should be able to evaluate these things, cotangent of pi/3 and cotangent of pi/6, without much effort, and certainly without a calculator. There are many ways you might do it in your mind, but if all else fails, just draw a 30, 60, 90 triangle and read the ratios off of that. Here's our triangle. We call the short side 1, and just remember that this is half of an equilateral triangle, and each side of that equilateral triangle must be 2. That means this hypotenuse must be 2, which means this other leg must be, by the Pythagorean theorem, the square root of 3. So what's the cotangent of pi over 3? Well, pi over 3 is 60 degrees. So the cotangent of this angle, cotangent is the reciprocal of tangent. Tangent is opposite over adjacent. So that's root 3 in this case. That means the cotangent would be 1 over root 3. And what about the cotangent of pi over 6? That's 30 degrees. Here's 30 degrees. Cotangent is the reciprocal of tangent. The tangent of 30 degrees, opposite over adjacent, is 1 over root 3. So its reciprocal, the cotangent, is root 3 over 1, or in other words, root 3. This can be cleaned up a little bit by combining the related terms, and we end up with this stuff. There's not much we can do to simplify that. This maybe we could clean up a little bit. If we rationalize the denominator here, then it would be pretty easy to combine these, I think. Let's see. If we rationalize the denominator here, we get 2 root 3 over 3. Oh yeah, that helps. This is 2 copies of square root of 3 minus 2/3 of a copy. Well, 2 is, what, 6/3? Take away 2 of them and we get 4/3. So all that becomes 4/3 root 3. That certainly looks a lot nicer than this one, so that was well worth our time. If you want, we could go one step further, factor out 1/3 from both of those things and write it as that stuff. Either of these look good. They're both on the same basic order of complexity. All right, so much for the linearity properties, whether of antiderivatives or of integrals. I want to mention one other algebraic property of integrals, which is sometimes a useful thing to know. So consider a general integral, and let's think about what would happen to it if we were to swap the boundaries of integration so that we ended up with this. So instead of integrating f from a to b, we would integrate f from b to a. What's the relationship between those two integrals? At first you might think, well, shouldn't they be the same? Because we're adding up the same stuff over the same interval, a to b or b to a, what difference does it make? Well, the only difference actually has to do with the dx's. This is subtle. If we have our function f and we're looking at the interval from a to b, think about what our hardworking integration demon does to evaluate this integral. Well, he flies down to a, zips across from a to b. At each little spot, he takes an infinitesimal step, gets that infinitesimal change in x, weights it with the value of f of x there, puts the result in his little book, does this at every point, keeping a running total of his results, and when he gets to b, he stops and he's done. If we asked him to do this, it would be the same thing, except he'd fly in at the other end and go from b to a. There's one tiny difference, though, as I said, with the dx's. When he's going this way, the normal way, those dx's are positive infinitesimal changes because the value of x is increasing as he goes that way. He takes an infinitesimal step in the positive direction. So the change in x is positive. If he's going from b to a, this weird backwards way, he's still hitting all the same values of the function in reverse order, but he's still hitting them all. But his dx's are all negative infinitesimals because each little infinitesimal step he takes yields a infinitesimal decrease in the value of x. So all these f of x dx's are almost mirrored by all of these f of x dx's. The only difference is each one of these has a negative factor. So that means if they're positive here, they'd be negative here, and vice versa. The difference being that whatever total we get here, we'll get a total of the exact same magnitude here, but with the opposite sign, because of that little negative factor that is tucked into every single one of those f of x dx's. So the result I'm looking for here is that if you reverse the order of integration, you end up with a factor of -1. You get a minus before the integral sign. This is an occasionally useful property to note. Not so much for evaluating individual integrals, but sometimes if we're combining integrals in different ways. Like if we ever came across an expression like this, the integral of some function f from 1 to 2 minus the integral of that same function f from 3 to 2. Well, you might think, oh, do the linearity properties help me here? Not so much, because I have different boundaries of integration on each integral. But this property can help me a little bit. Let's rewrite this second integral. Instead of integrating f from 3 to 2, I know that I can reverse those boundaries if I change the sign of the integral. So I could write this whole thing as the first integral, and instead of subtracting the second one, add it, which we can do if we reverse the order of the boundaries of integration. Why does that help us? I mean, sure, pluses are nicer than minuses, but is there anything beyond that? There is. We can make perfect sense of this, because here we are integrating f from 1 to 2, so adding up all those f of x dx dx's as we go from 1 to 2, and then we're adding up all the f of x dx's as we go from 2 to 3. Well, what's the net result of that? Obviously, the net result is that we're adding up all those f of x dx's as we go from 1 to 3. Now that is a much nicer expression than what we started with. All right, I think this one has gone on long enough, and we are now at the end of Chapter 4 and ready to move on into Chapter 5, which will be entirely devoted to the problem of finding antiderivatives so that we can use this fundamental theorem of calculus to evaluate integrals. So that's all, folks. See you next time.